We've talked a lot about activities and how they related to concentration, namely the activity would be an activity coefficient times concentration. Let's consider now how one actually measures activity coefficients. All right, so we talked about activity coefficients. They're essentially a correction factor so that when you calculate thermodynamic quantities, you're using concentration, but the concentration is not as active as before, so you put in this fudge factor, the activity coefficient, in order to correct the concentrations to get the right thermodynamic properties. But actually, how do we measure those? An easy way to do that is use electrochemical measurements. Because electrochemical measurements, what you do is get activities. Electrochemical measurements will always give you activities, and then you figure out how much concentration you had to add to the electrochemical cell to get that activity, and then the ratio of those will just be the activity coefficient. All right, and then I'll return to this point in just a second, but let's do an example. Let's construct an electrochemical cell, and let's measure a voltage, and let's measure the activity coefficient of HCl. Well, let's first talk about what that cell looks like. Electrochemical cells. So maybe you remember from introductory chemistry, typically you have a half reaction, and the two half reactions are separated in two different beakers, and you electrically connect these two beakers with a salt bridge. Maybe you remember that. So this is a salt bridge. And then for this particular example, let's over here make a standard hydrogen electrode. So that's called SHE. So standard hydrogen electrode, what does that look like? Well, I'm not very good at drawing, but thank goodness for the internet. So here's a picture from this particular web page of a standard hydrogen electrode. So remember the standard hydrogen electrode, what you're doing is taking H plus and for the reduction reaction, sticking two electrons on that to make H2. So let's take a look at that. Here we go. So hydrogen gas is coming in here. This you might recognize as 1 atmosphere. Why are we using 1 atmosphere? Well, we want the standard potential, and by convention, the standard potential is like for standard conditions is 1 atmosphere, which is 101.325 kilopascal, or 101,325 Pascal. All right, so that's what that is. So you have 1 atmosphere coming in here, and the water is bubbling, or sorry, the hydrogen gas is bubbling through the water. This is a water solution. And here you have a particular kind of platinum, and that's what gives you the electrical connection. So at the platinum, the molecular reaction of H2 breaking apart to H plus, and the electrons being flowing around here, that happens right there at the platinum electrode. Okay, so that's what I'm trying to draw over here. That's the platinum standard hydrogen electrode. And over here, let's put a silver-silver chloride electrode, a silver-silver chloride electrode. A silver-silver chloride electrode, you have a piece of silver wire, and here you've deposited on the silver wire some silver chloride. And you'll learn more detail about this, presumably in Chem 422, Instrumental Analysis, if you decide to take that course in your BA major. You have to take it if you're BS. All right, so let's write the half reactions that are going on here. And by the way, you probably remember in introductory, you don't have to always draw this out. Here's an easier way. You use this shorthand notation, platinum solid. So we're going over here left to right. That means you have difference in phase. You have H2 gas, and we have 1 atmosphere. So that's the standard condition. So this is a standard hydrogen electrode. Oh, we have to put some electrolyte in here. Let's make HCl. So that's dissolved in water into H plus ions and Cl ions. And then over here we'll have the silver chloride, and here we'll have the silver. So that's a shorthand way of writing this. If we write the half reactions, let's just do it here, 1/2 H2. this will go to H+, and that'll give out one electron, which will flow up through here. And then for the silver chloride, we'll stick on one electron on the silver in the silver chloride. So silver is a +1 charge, and so you're going to add one electron to that to make silver solid and chloride aqueous, assuming this is water. And this, by the way, you should always put the state here, gas. This would be aqueous. All right, so our overall reaction then will be silver chloride plus 1/2 H2 goes to silver, and I should put solid gas solid plus H plus aqueous plus Cl minus aqueous. Now these are actually good electrodes, and everybody uses these electrodes. Why is that? Well, you really don't need that salt bridge. You can actually put in the solution your standard hydrogen electrode and your silver chloride. And here you just have H plus and Cl minus, HCl in solution. Why is that? Well, here's the platinum electrode. That's just a different phase, and so all the electrons go there. And this is silver chloride, all solids. So you really don't need to separate these two because everything happens on these different phases, solid phases. So that's why this is particularly particularly useful and popular. And I should say, of course, you put in some voltmeter to measure the cell voltage. You want to measure the cell voltage. All right, so that's you really don't need the salt bridge. You just put everything in here because, in contrast to say the zinc and copper system we had before, there that you could actually play it out. Here, yeah, you have gas here. Here you have solids. Here you have aqueous solutions. This is an easy cell to make. All right. So anyway, this is the cell that that this example refers to. Okay, so, I forgot to say what the concentration is there. So the concentration of HCl in this slide is 0.10 molar. Okay, so typically what you do when you're drawing this, and actually let me just go ahead and redraw this. This will be 0.10 molar, which then goes to silver chloride, then goes to silver solid. All right, so there's our concentration. I forgot to put that in the problem. So you put, let's just ignore this for now, and the solution concentration is 0.1 molar. Why am I using molar instead of molal or mole fraction or so on? The reason I'm doing that is if you look at standard electrode potentials, if I'm going to use this table of standard electrode potentials, reduction potentials, to calculate E0, I have to have this standard state. This standard refers to this standard state. So if you're going to do an experiment and you're going to use standard state, reduction potentials, you got to make this standard state. Standard state means specify units. Units here, by convention, 1 mole per liter or 1 molar, M-O-L-A-R, and this is 1 atmosphere for hydrogen. All right, so that's why we express this in terms of molar concentration. Okay, so there we have everything. So let's see if we can calculate the activity coefficient for that. Well, we'll start with the Nernst equation. The Nernst equation, cell voltage is the standard state cell voltage minus RT over NF times the natural log of the reaction quotient Q. Well, let's express the reaction quotient Q in terms of activity. So it's RT over NF. For this particular reaction, we're taking the activity, the products, that was the activity of silver, solid silver, the activity of H plus, and the activity of Cl minus. Those are the products. We're going to divide by the activity of the reactants. The reactants were silver chloride and H2, but remember the stoichiometric coefficient and the balanced chemical reaction in front of H2 was 1/2. Well, this can be considerably simplified, realizing that the activity of silver is equal to 1. Presume we have pure solid silver. The activity of silver chloride, if you have pure silver chloride, that's a solid, that's equal to 1. And the activity of H2 is equal to 1 because H2 is at the standard state. Standard state was 1 atmosphere, so the activity is 1. So this expression considerably simplifies into standard state cell voltage RT over NF times the natural log of the activity of H plus times the activity of Cl minus. And also note that there's one electron being transferred here, so N is equal to 1. So we can rewrite this a little more simply here as E is equal to E0 minus RT over F times the natural log of the activity of H plus times the activity of Cl minus. Now, a few lectures ago, we decided that, in fact, we can't measure the activity of just a single ion in solution, although in the next section we'll find that, well, maybe we can. But just for now, let's say we can't measure individually these activities. Instead, what we have to do is to use mean activities and mean activity coefficients. So if we look up in the previous lecture, we can define a mean activity, A plus minus, for HCl. That will be the activity coefficient plus minus times the concentration, the average concentration plus minus, divided by the standard concentration, and we're using molar since we can use E0. E0 table has for a standard state 1 molar, and this whole thing is raised to the 1/2 power. And similarly, we have the mean activity coefficient gamma plus minus. That's equal to the activity of H plus times the activity of Cl minus to the 1/2. That's the geometric mean. And similarly, M plus minus, what does that mean? Well, that's the molality of the, or molarity of the plus charges, that's MH plus, times the molarity of the minus charges, raised to the 1/2. But since the only source of H and Cl in this experiment is from HCl, this is just equal to the molar concentration of HCl. All right. Then once we have these mean activities, mean activity coefficients, mean concentrations defined, then we replace the activity of H plus to be the mean activity times the average concentration, M plus minus, and the activity of Cl minus is the mean activity, which we calculated above here, times the molality plus minus. So switching from the activities of individual ions to activities, mean activities, we can rewrite the Nernst equation as E is equal to E0 minus RT over F, we're saying N is equal to 1, times the natural log of the average activity squared times the average molarity, M plus minus, squared. Each one of these you get a term for the H, a term for the Cl, and therefore when we replace the averages we get the squared. So we can rearrange this equation a little bit. Well, let's just do a few steps here. E0 minus RT over F times natural log of gamma plus minus squared plus natural log of M plus minus squared. Logarithm of product is the sum of the logarithms. We solve this for the, what do we want? We're trying to measure the mean activity coefficient of HCl. So what we want is to isolate that. The mean activity, natural log squared, is just equal to minus E minus E0. I'm just solving this equation for this term here, times F. Well, actually, let's make it a little simpler. So let's divide this by RT over F. And then we subtract off this the natural log of M plus minus squared. Now remember, RT over F, we did a calculation, RT over F at 25 degrees C in SI units is equal to 0.02568. Okay. Volts. So, what is E for the cell and E0 for the cell? Well, E for the cell, as given in the problem, was actually my calculations here are a little different. So let's give you what the E is actually measured: 0.352 volts. E0 for this cell. Remember, we're measuring it against the standard hydrogen electrode, which we set to be equal to 0. So, in fact, the standard voltage would just be, let's see if we can find it here. Standard electrode voltages. Here we go. Silver chloride going to silver. So we're putting one electron on that Ag plus to make silver. 0.22233. That's reduction potential. And we're referencing that against the standard hydrogen electrode, which is 0. So E0 for this would be 0.22233. If you take instrumental analysis, you'll find that, well, really we should calculate or measure E0 under the conditions of the experiment. So this is, even though it is a 1 molar standard state, we should nonetheless measure E0. Take 422 instrumental analysis for more details on this. But for this type of calculation, just let's say this E0 is good, doesn't depend upon the concentrations and so on. All right, RT over F, like that. And then we said that M plus minus squared, that's just equal to the concentration, 0.1 molar squared. So we can plug all these numbers into here and solve for the natural log of the mean activity coefficient squared. That comes out to be minus 0.444. So that the mean activity coefficient squared is e to that number. That is 0.641. Or finally, the mean activity coefficient of HCl in the 0.1 molar solution is, is 0.801. So that's how one calculates mean activity coefficients from electrochemical measurements.